The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
I'm going to get started right away. I want to make a comment about energy, time, uncertainty relations. And we talked last time about the fact that the energy, time, uncertainty relation really tells you something about how fast a state can change. So an interesting way to try to evaluate that is to consider a system that has a state at time equals 0 and compute the overlap with the state at time equal t. Now, this overlap is a very schematic thing. It's a bracket, it's a number, and you know what that means. You can keep in mind what that is. It's an integral over space, possibly, of psi star at t equals 0 x psi at t x. It's a complete integral. It's the inner product. So you may want to understand this because, in a sense, this is telling you how quickly a state can change. It's at time equals 0, this overlap is just 1. A little later, this overlap is going to change, and perhaps after some time, the overlap is going to be 0, and we're going to say that we actually have changed a lot. So this number is very interesting to compute, and in fact, we might as well square it because it's a complex number. So to understand better what it is, we'll square it, and we have to evaluate this. Now, how could you evaluate this? Well, we'll assume that the system that governs this time evolution has a time-independent Hamiltonian. Once this evolution is done by a time-independent Hamiltonian, you can wonder what it is. Now, it's quite interesting, and you will have to discuss that in the homework because it will actually help you prove that version of the time energy uncertainty relationship that says that the quickest time a state can turn orthogonal to itself is bounded by some amount. Cannot do it infinitely fast. So you want to know how fast this can change. Now, it's very surprising what it depends on, this thing, because suppose you had an energy eigenstate. Suppose psi at time equals 0 is an energy eigenstate. What would happen later on? Well, you know that energy eigenstates evolve with a phase, an exponential of e to the minus I ht over h bar. So actually, if you had an energy eigenstate, this thing would remain equal to 1 for all times. So if this is going to be non-zero, it's because it's going to have, you have to have a state that is not an energy eigenstate, that you're going to have an uncertainty in the energy, energy uncertainty. So the curious thing is that you can evaluate this and expand it as a power in t, and go, say, to quadratic order in t, evaluate what this is, and this only depends on the uncertainty of h and t and things like that. So only the uncertainty of h matters at this moment. So this will be quite interesting, I think, for you to figure out and to explore in detail. That kind of analysis has been the center of attention recently, having to do with quantum computation, because in a sense, in a quantum computer, you want to change states quickly and do operations. So how quickly you can change a state is crucial. So in fact, the people that proved these inequalities that you're going to find say that this eventually will limit the speed of a quantum computer. And you know Moore's law that computers become twice as fast every year or so, and they double the speed. So this limit, apparently, it's claimed that will allow 80 duplications of the speeds until you hit this limit in a quantum computer, and due to quantum mechanics. So you will be investigating this in next week's homework. Today, we want to begin quickly with an application of the uncertainty principle to find exact bounds of energies for quantum systems, for ground states of quantum systems. So this will be a very precise application of the uncertainty principle. Then we'll turn to a completion of these things that we've been talking about having to do with linear algebra. We'll get to the main theorems that of the subject. In a sense, the most important theorems of the subject. These are the spectral theorem that tells you about what operators can be diagonalized, and then a theorem that leads to the concept of a complete set of commuting observables. So really pretty key mathematical ideas. And the way we're going to do it, I think you will see that we have gained a lot by learning the linear algebra concepts in a slightly abstract way. I do remember doing this proof that we're going to do today in previous years, and it was always considered the most complicated lecture of the course. Just the indices went crazy, and lots of formulas, and the notation was funny. And now we'll do the proof, and we'll write a few little things, and we'll just try to imagine what's going on, and will be, I think, easier. I hope you will agree. So let's begin with an example of a use of the uncertainty principle. So example. So this will be maybe for 20 minutes. Consider this Hamiltonian for a one-dimensional particle that, in fact, you've considered before, alpha x to the fourth, for which you did some approximations. And you knew that the expectation value of the energy in the ground state, you've done it numerically, you've done it variationally, and variationally you knew that the energy at every stage was smaller than a given bound. The uncertainty principle is not going to give us an upper bound. It's going to give us a lower bound. So it's a really nice thing, because between the variational principle and the uncertainty principle, we can narrow the energy of this ground state to a window. In one of the problems that you're doing for this week, and I'm sorry, only today you really have all the tools, if after you'll hear this discussion, you do the same for the harmonic oscillator. You do the variational estimate for the ground state energy. You do the uncertainty principle bound for the ground state energy, and you will see these two bounds meet. And therefore, after you've done these two bounds, you found the ground state energy of the harmonic oscillator. So it's kind of a neat thing. So we want to estimate the ground state energy. So we first write some words. We just say h in the ground state will be given by the expectation value of p squared in the ground state plus alpha times the expectation value of x to the fourth in the ground state. Haven't made much progress, but you have, because you're starting to talk about the right variables. Now, the things that you have to know is that you have a potential that is like this, sort of a little flatter than a x squared potential. And what can we say about the expectation value of the momentum on the ground state and the expectation value of x in the ground state? Well, the expectation value of x should be no big problem. This is a symmetric potential. Therefore, wave functions in a one-dimensional quantum mechanics problems are either symmetric or antisymmetric. It could not be antisymmetric because it's a ground state and cannot have a zero, so it's a symmetric, has no nodes. So there's the wave function of the ground state is symmetric, and the expectation value of x in the ground state is 0. Similarly, the expectation value of the momentum in the ground state, what is it? Is 0 too. And you can imagine just computing it. It would be the integral of psi. Psi is going to be real dx h bar over I psi. This is a total derivative. If it's a bound state, it's 0 at the ends. This is 0. So actually, we have a little advantage here. We have some control over what p squared is because the uncertainty in p in the ground state, well, the uncertainty in p squared is the expectation value of p squared minus the expectation value of p squared. So in the ground state, this is 0. So delta p squared in the ground state is just p squared on the ground state. Similarly, because the expectation value of x is equal to 0, delta x squared in the ground state is equal to expectation value of x squared in the ground state. So actually, this expectation value of p squared is delta p, and we want to use the uncertainty principle, so that's progress. We've related something we want to estimate to an uncertainty. The small complication is that we have expectation value of x to the fourth. Now, we learned, maybe I can continue here. We learned that the expectation value of an operator squared is bigger than or equal to the expectation value of the operator squared. So the expectation value of x to the fourth is definitely bigger than the expectation value of x squared squared. And this is true on any state. This was derived when we did uncertainty. We proved that the uncertainty squared is positive because it's the norm of a vector, and that gave you this thing. So here you think of the operator as x squared. So the operator squared is x to the fourth, and here's the operator, expectation value squared. So this is true for the ground state. It's also here true for any state. So is the ground state. And this x squared now is delta x. So this is delta x on the ground state to the fourth. So look what we have. We have that the expectation value of h on the ground state is strictly equal to delta p on the ground state squared over 2m plus alpha. And we cannot do a priori inequality here, so we have this. This is so far an equality. But because of this thing is bigger than that. Well, alpha is supposed to be positive, so this is bigger than delta p ground state squared over 2m plus alpha delta x on the ground state to the fourth. Okay, so far so good. We have a strict thing, this, and the order of the inequality is already showing up. We're going to get, if anything, a lower bound. You're going to be bigger than or equal to something. So what is next? Next is the uncertainty principle. We know that delta P, delta X is greater than or equal to h bar over 2 in any state. So delta P ground state and delta X on the ground state still should be equal to that. Therefore, delta P ground state is bigger than or equal than h over 2 delta X in the ground state, like that. So this inequality is still the right direction. So we can replace this by something that is bigger than this quantity without disturbing the logic. So we have h ground state now is greater than or equal to, replace the delta P by this thing here, h squared over 8, because this is squared and there's another 2, m delta X ground state squared plus alpha delta X ground state to the 4th. And that's it. We've obtained this inequality. So here you say, well, you know, this is good, but how can I use it? I don't know what delta X is in the ground state, so what have I gained? Well, let me do a way of thinking about this that can help you. Plot the right-hand side as a function of delta X on the ground state. You don't know how much it is, delta X on the ground state, so just plot it. So if you plot this function, there will be a divergence as this delta X goes to 0. Then it will be a minimum. It will be a positive minimum because this is all positive, and then it will go up again. So the right-hand side as a function of delta X is this. So here it comes. You see, I don't know what delta X is. Suppose delta X happens to be this. Well, then I know that the ground state energy is bigger than that value. But maybe that's not delta X. Delta X maybe is this on the ground state. And then if it's that, well, the ground state energy is bigger than this value over here. Well, since I just don't know what it is, the worst situation is if delta X is here, and therefore definitely H must be bigger than the lowest value that this can take. So the claim is that H of GS therefore is greater than or equal than the minimum of this function h squared over 8m, and I'll just write here delta x squared plus alpha delta x to the 4th over delta x. The minimum of this function over that space is the bound. So I just have to do an arithmetic, a calculus problem here. This is the minimum. I should take the derivative with respect to delta x, find delta x, and substitute. Of course, I'm not going to do that here, but I'll tell you a formula that will do that for you. A over x squared plus b x to the 4th is minimized for x squared is equal to 1 over 2. It's a pretty awful numbers. 2 to the 1/3, a over b to the 1/3. and its value at that point is 2 to the 1/3 times 3/2 times a to the 2/3 times b to the 1/3. A little bit of arithmetic. Let me. So for this function, it turns out that a is whatever coefficient is here, b is whatever coefficient is there, so this is supposed to be the answer. And you get h on the ground state is greater than or equal to 2 to the 1/3, 3/8, h squared square root of alpha over m to the 2/3, which is about 0.4724 times h squared square root of alpha over m to the 2/3. And that's our bound. How good or how bad is the bound? It's okay. It's not fabulous. The real answer that is done numerically is with 0.668. I think I remember the variational principle gave you something like 0.68 or 69. And this one says it's bigger than 0.47. It gives you something. So the important thing is that it's completely rigorous. You know, many times people use the uncertainty principle to estimate ground state energies. Those estimates are very hand-wavy. You might as well just do dimensional analysis. You don't gain anything. You don't know the factors. But this is completely rigorous. I never made an approximation or anything here. Every step was logical. Every inequality was exact. And therefore, this is a solid result. This is definitely true. It doesn't tell you an estimate of the answer. You see, if you do dimensional analysis, you say the answer is this times 1. And that's as good as you can do with dimensional analysis. It's not that bad. The answer turns out to be 0.7. But the uncertainty principle really, if you're careful, sometimes, not for every problem, you can do a rigorous thing and find a rigorous answer. Okay, so are there any questions? Your problem in the homework will be to do this for the harmonic oscillator and find the two bounds. Yes?
How does the answer change if we don't look at the ground state?
How did I what?
How does the answer change if we look at a state different from the ground state?
Different from the ground states? So the question was, how would this change if I would try to do something different from the ground state? I think for any state, you would still be able to say that, that the expectation value of the momentum is 0. Now, the expectation value of x still would be 0, so you can go through some steps here. The problem here being that I don't have a way to treat any other state differently. So I would go ahead and I would have said for any stationary state or for any energy eigenstate, all of what I've said is true. So I don't get a new one. You know, these things, people actually keep working and writing papers on this stuff. People sometimes find bounds that are a little original. Yes?
How do you know the momentum expectation is 0 again?
The momentum expectation for a bound state goes like this. So you want to figure out what is psi, p psi, and you do the following. That's integral of, now psi in these problems can be chosen to be real, so I won't bother. It's psi of x h bar over I ddx of psi. So this is equal to h bar over 2I, the integral dx of d dx of psi squared. So at this moment, you say, well, that's just h bar over 2I, the value of psi squared at infinity and at minus infinity. And since it's a bound state, it's 0 here, 0 there, and it's equal to 0. You know, a state that would have expectation value of momentum, you would expect it to be moving. So this state is there, it's static, it's stationary. It doesn't have expectation value of momentum. Yes?
Is the reason that you can't get a better estimate for the things that are in the ground state? Because like, if you consider the harmonic oscillator, the uncertainty delta x delta b is saturated for the ground state. It's worse as you go up to higher states.
Right, I think that's another way.
There's no way to distinguish higher state using the absolute.
Yeah, that's the point. So the ground state of the harmonic oscillator saturates the uncertainty principle and the others don't. So this argument, I think, is just good for ground state energies. One more question.
So it appears that this method really doesn't particularly work well if we have a potential that it has an odd power, because we can't use the fact that like x to the expectation value of x to the 4 is something, some power expectation.
Right. If it's an odd power, the method doesn't work well. But actually, for an odd power, the physics doesn't work well either, because the system doesn't have ground states. And so let's say that if you had x to the 4th plus some x cubed, the physics could still make sense. But then it's not clear I can do the same. Actually, you can do the same for x to the 8 and any sort of powers of this type, but I don't think it works for x to the 6. You can try a few things. OK, so we leave the uncertainty principle and begin to understand more formally the operators for which there's no uncertainty and you can simultaneously diagonalize them. So we're going to find operators that are like A and B, that they commute, and then sometimes you can simultaneously diagonalize them. Yes, you have a question.
So, okay, part of the logic we use here is the uncertainty principle, right?
Right.
If we get an answer, is there any way that we can better our uncertainty principle based on the wave function we've not saturated? Can we get an upper bound for the uncertainty principle than h bar?
Can I get an upper bound? I'm not sure I understand your question.
The fact that like the uncertainty principle will not be saturated, can you put the bound for the uncertainty above h bar?
You know, this is certainly. You might have some systems in which you know that this uncertainty might be bigger than the one guaranteed by the uncertainty principle. So then you use that information. But on general grounds, it's hard to know that a system might come very close to satisfy the uncertainty principle in its ground state. We don't know. There are systems that come very close in the ground state to satisfy this and some that are far. If they are far, you must have some reason to understand that to use it. So I don't know. So let me turn to this issue of operators and diagonalization. So diagonalization of operators. Now, you might be irritated a little even by the title, diagonalization of operators. Shouldn't you be talking about diagonalization of matrices? Well, there's a way to state what we mean by diagonalizing an operator in such a way that we can talk later about the matrix. So what is the point here? You have an operator, and it's presumably an important operator in your theory. You want to understand this operator better. So you really are faced with a dilemma. How do I get some insight into this operator? Perhaps the simplest thing you could do is to say, OK, let me choose some ideal basis of the vector space such that the operator is as simple as possible in that basis. So that's the origin of this thing. Find a basis in the state space so the operator looks as simple as possible. So you say that you can diagonalize an operator if you can find a basis such that the operator has just diagonal entries. So let me just write it like this. So if you can find a basis in V where the matrix representing the operator is diagonal, the operator is said to be diagonalizable. So to be diagonalizable is just a statement that there is some basis where you look at the matrix representation operator and you find that it takes form as a diagonal. So let's try to understand this conceptually and see what actually is telling us. It tells us actually a lot. Suppose T is diagonal in some basis U1 up to UN. So what does it mean for it to be diagonal? Well, you may remember all these definitions we had about matrix action. If T acting on a UI is supposed to be T, K, I, U, K in some basis, sum over K. You act on UI, and you get a lot of U's, and these are the matrix elements of the operator. Now, the fact that this diagonalizable means that in some basis, the U basis, this is diagonal. So Ki in this sum only happens to work out when K is equal to I, and that's one number, and you get back the vector Ui. So this, if it's diagonal in this basis, you have that T on U1 is lambda, a number, times U1. T on U2 is lambda 2 in U2. And T UN equal lambda n UN. So what you learn is that this basis vector, so you learn something that maybe you thought it's tautological, but it's not quite tautological. You learn that if you have a set of basis vectors in which the operator is diagonal, these basis vectors are eigenvectors of the operator. And then you learn something that is quite important, that an operator is diagonalizable if and only if it has a set of eigenvectors that span the space. So the statement is very important. An operator T is diagonalizable if it has a set of eigenvectors that span the space on V. If and only if this double F, if and only if. So here it's diagonalizable, and we have a basis, and it has a set of, these are eigenvectors. So diagonalizable really means that it has a set of eigenvectors that span the space. On the other hand, if you have the set of eigenvectors that span the space, you have a set of U's that satisfy this, and then you read that, oh yeah, this matrix is diagonal, so it's diagonalizable. So a simple statement, but an important one, because there are examples of matrices that immediately you know you're never going to succeed to diagonalize. So here is one matrix, 0, 0, 1, 0. This matrix has eigenvalues. You do the characteristic equation, lambda squared equals 0. So the only eigenvalue is lambda equals 0. And let's see how many eigenvectors you would have for lambda equals 0. Well, you would have, if this is t on some vector a, b must be equal to 0. So this is 0, 1, 0, 0 on a, b, which is b and 0 must be 0. So b is equal to 0. So the only eigenvector here, I'll just write it here and then move to the other side. The only eigenvector for lambda equals 0, the only eigenvector is with b equals 0, so it's 1, 0. One eigenvector only, no more eigenvectors. By this theorem, or by this claim, you know it's a two-dimensional vector space. You just can't diagonalize this matrix. It's impossible. Can't be done. Okay, a couple more things that I wish to say about this process of diagonalization. Well, the statement that an operator is diagonal is a statement about the existence of some basis. Now, you can try to figure out what that basis is. So typically, what is the problem that you face? Typically, you have a vector space V. Sorry? Yes?
If you have an infinite dimensional space, and you have an operator whose eigenvectors do not span the space, can it still have eigenvectors, or does it not have any then?
No, you said it has some eigenvectors, but they don't span the space. So it does have some eigenvectors.
So my question is, was what I just said a logical contradiction in an infinite dimensional space?
To have just some eigenvectors? I think...
I mean, I'm looking more specifically at like a dagger, for instance.
Yes.
In the harmonic oscillator, you, I think, mentioned at some point that it does not have.
Right. So the fact that you can't diagonalize this thing already implies that it's even worse in higher dimensions. So some operator may be pretty nice, and you might still not be able to diagonalize it. So you're going to lack eigenvectors in general. You're going to lack lots of them, and there's going to be blocks of Jordan blocks are called, things that are above the diagonal, things that you can't do much about. Let me then think concretely now that you have a vector space and you've chosen some basis, V1, Vn, and then you look at this operator T, and of course, you chose an arbitrary basis. There's no reason why its matrix representation would be diagonal. So T on the basis V, Tij, sometimes to be very explicit, we write Tij like that, is not diagonal. Now, if it's not diagonal, the question is whether you can find a basis where it is diagonal, and then you try, of course, changing basis, and you change basis, you've discussed that in the homework, with a linear operator. So you use a linear operator to produce another basis, an invertible linear operator. so that you get vectors uk being equal to some operator A times vk. So this is going to be the u1s up to un's are going to be another basis. The vector, the nth vector here is the operator acting with the n vector on this thing. And then you prove that the homework a relationship between this matrix elements of T in the new basis, in the U basis, and the matrix elements of T in the V basis. You have a relationship like this, or you have more explicitly T ij in the basis U is equal to A minus 1 I k T k P of V A P J. So this is what happens. This is the new operator in this basis, and typically what you're trying to do is find this matrix A that makes this thing into a diagonal matrix, because we say in the U basis the operator is diagonal. I want to emphasize that there's a couple of ways in which you can think of diagonalization, sort of a passive and an active way. You can imagine the operator, and you say, look, this operator, I just need to find some basis in which it is diagonal. So I'm looking for a basis. The other way of thinking of this operator is to think that A minus 1 T A is another operator, and it's diagonal in the original basis. So it might seem funny to you, but let's stop again and say this again. You have an operator, and the question of diagonalization is whether there is some basis in which it looks diagonal, its matrix is diagonal. But the equivalent question is whether there is an operator A such that this is diagonal in the original basis. To make sure that you see that, consider the following. So this is diagonal in the original basis. So in order to see that, think of T ui is equal to lambda I ui. We know that the u's are supposed to be this basis of eigenvectors where the matrix is diagonal. So here you got it. Here the I is not summed. It's pretty important. There's a problem with this eigenvalue notation. I don't know how to do it better. If you have several eigenvalues, you want to write this, but you don't want this to think that you're acting on U1, then you get lambda 1, U1, not the sum in here. OK, but the UI is equal to A on VI. So therefore, this is lambda I A on VI. And then you act with A minus 1. Act with A minus 1 from the left with the operator. So you get A minus 1 T A VI is equal to lambda I VI. So what do you see? You see an operator that is actually diagonal in the V basis. So this operator is diagonal in the original basis. That's another way of thinking of the process of diagonalization. There's one last remark, which is that the columns of A are the eigenvectors, in fact. Columns of A are the eigenvectors. Well, how do you see that? You say it's really very simple. You can convince yourself in many ways, but the UK are the eigenvectors. But what are UKs? I have it somewhere there. There is A on VK. And A on VK is this matrix representation, is sum over I, A, I, K, VI. So now, if this is the original basis, the VI's are your original basis, then you have the following, that the VI's can be thought as the basis vectors and represented by columns with a 1 in the ith entry. So this equation is saying nothing more or nothing less than UK in terms of matrices or columns, UK is equal to A1KV1 plus ANKVN, which is just A1K, A2K, ANK. Because VI is the ith basis vector, so 1, zeros, only in the ith position. So these are the eigenvectors, and they're thought as linear combinations of the VI's. The VI's are the original basis vectors, so the eigenvectors are these numbers. Okay. We've talked about diagonalization, but then there's a term that is more crucial for our operators that we're interested in. We're talking about Hermitian operators. So the term that is going to be important for us is unitarily diagonalizable. What is a unitarily diagonalizable operator? Two ways, again, of thinking about this, and perhaps the first way is the best, and I will say it. A matrix is said to be unitarily diagonalizable if you have an orthonormal basis of eigenvectors. All of it. You know, remember, diagonalizable meant a basis of eigenvectors. That's all it means. Unitarily diagonalizable means orthonormal basis of eigenvectors. So T has an orthonormal basis of eigenvectors. Now, that's a very clear statement. And it's a fabulous thing if you can achieve, because you basically have broken down the space into basis spaces. Each one of them is a simple thing for your operators, and they're orthonormal. So it's the simplest possible calculational tool. So it's ideal if you can have this. Now, the way we think of this is that you start with, concretely, you start with a T of some basis V that is an orthonormal basis. Start with an orthonormal basis, and then pass to another orthonormal basis u. So you're going to pass to another orthonormal basis u with some operator. But what you have learned is that if you want to pass from V orthonormal to another basis u of vectors that is also orthonormal, the way to go from one to the other is through a unitary operator. Only unitary operators pass you from orthonormal to orthonormal basis. Therefore, really, when you start with your matrix in an orthonormal basis that is not diagonal, the only thing you can hope is that T of u will be equal to some u dagger, or u minus 1, T of v, u. Remember, for a unitary operator, where u is unitary, for a unitary operator, the inverse is the dagger. So you're doing a unitary transformation, and you find the matrix that is presumably then diagonal. So basically, unitarily diagonalizable is the statement that if you start with the operator in an arbitrary orthonormal basis, then there's some unitary operator that takes you to the privileged basis in which your operator is diagonal. It's still orthonormal, but maybe in a more simple way, unitarily diagonalizable is just the statement that you can find an orthonormal basis of eigenvectors. Now, the main theorem of this subject, perhaps one of the most important theorems of linear algebra, is the characterization of which operators have such a wonderful representation. What is the most general thing what is the most general operator T that will have an orthonormal basis of eigenvectors? Now, we probably have heard that Hermitian operators do the job. Hermitian operators have that. But that's not the most general ones. And given that you want the complete result, let's give you the complete result. The operators that have this wonderful property are called normal operators, and they satisfy the following property. M is normal if M dagger, the adjoint of it, commutes with M. So Hermitian operators are normal because M dagger is equal to M, and they commute. Anti-Hermitian operators are also normal because anti-Hermitian means M dagger is equal to minus M, and it still commutes with M. Unitary operators have U dagger U equal to U dagger equals to 1. So U and U dagger actually commute as well. So Hermitian, anti-Hermitian, unitary, they're all normal operators. What do we know about normal operators? There's one important result about normal operators, a lemma. If M is normal and X is an eigenvector, if and W is an eigenvector such that MW is equal to lambda W. Now, normal operators need not have real eigenvalues because they include unitary operators. So here I should write Hermitian, anti-Hermitian, and unitary are normal. So here is what a normal operator is doing. You have a normal operator, it has an eigenvector with some eigenvalue. Lambda is a complex number in principle, then the following result is true. Then m dagger omega is also an eigenvector of m dagger, and it has eigenvalue lambda star. So now this is not all that easy to show. It's a few lines, and it's done in the notes. I ask you to see it. It's actually very elegant. You know, what is the usual strategy to prove things like that is to say, oh, I want to show this is equal to that, so I want to show that this minus that is 0. So I have a vector that is 0. What is the easiest way to show that it's 0? If I can show its norm is 0. So that's a typical strategy that you use to prove equalities. You say, oh, it's a vector that must be 0 is my equality. Let's see if it's 0. Let's find its norm, and you get it. So that's a result. So with this stated, we finally have the main result that we wanted to get to. And I will be very sketchy on this, and might be, the notes are complete, but I will be sketchy here. It's called the spectral theorem. Let M be an operator in a complex vector space. The vector space has an orthonormal basis of eigenvectors of M if and only if M is normal. So the normal operators are it. You want to have a complete set of orthonormal eigenvectors. Well, this will only happen if your operator is normal. End of story. Now, there's two things about this theorem. Is to show that if it's diagonalizable, it is normal. And the other thing is to show that if it's normal, it can be diagonalized. Of course, you can imagine the second one is harder than the first. Let me do the first one for a few minutes, and then say a couple of words about the second, and you may discuss this in recitation. It's a little mathematical, but it's all within the kind of things that we do, and really it's fairly physical in a sense. We're accustomed to do such kind of arguments. So suppose it's unitarily diagonalizable, which means that M, so if you have U minus or U dagger, M U is equal to a diagonal matrix, dm. I'm talking now matrices. So these are all matrices, a diagonal matrix. There's no basis-independent notion of a diagonal operator, because if you have a diagonal operator, it may not look diagonal in another basis. Only the identity operator is diagonal in all bases, but not a typical diagonal operator. So unitarily diagonalizable, as we said, you make it, it's gone somewhere here. You act with an inverse matrix this, and you get a diagonal matrix. So from this, you find that M is equal to U dm U dagger by acting with U on the left and with U dagger from the right. You solve for M, and it's this. So, and then M dagger is the dagger of this thing. So it's U dm dagger U dagger. The U's sort of remain the same way, but the diagonal matrix is not necessarily real, so you must put the dagger in there. And now M dagger M, to check that the matrix is normal, that commutator should be 0. So M dagger M, you do this times that, you get U d M dagger, U dagger U, that's 1, the M U dagger, and M dagger, you multiply the other direction, you get U d M dagger, U dagger. So the commutator of M dagger M is equal to U dm dagger dm minus dm dagger U dagger. But any two diagonal matrices commute. They may not be that simple diagonal matrices, are not the identity matrix, but for sure they commute. You multiply elements along the diagonal, so this is 0. So certainly, any unitarily diagonalizable matrix is normal. Now, the other part of the proof, which I'm not going to speak about, it's actually quite simple, and it's based on the fact that any matrix in a complex vector space has at least one eigenvalue. So what you do is you pick out that eigenvalue and its eigenvector and change the basis to use that eigenvector instead of your other vectors. And then you look at the matrix, and after you use that eigenvector, the matrix has a lot of zeros here and a lot of zeros here. And then the matrix has been reduced in dimension, and then you go step by step. So basically, it's the fact that any operator has at least one eigenvalue and at least one eigenvector. It allows you to go down. And normality is analogous to hermiticity in some sense. And the statement that you have an eigenvector generally tells you that this thing is full of zeros, but then you don't know that there are zeros here. And either normality or hermiticity shows that there are zeros here, and then you can proceed in lower dimensions. So you should look at the proof because it will make clear to you that you understand what's going on. Okay, but let's take it for granted now. You have these operators and can be diagonalized. Then we have the next thing, which is simultaneous diagonalization. What is simultaneous diagonalization? It's an awfully important thing. So we'll now focus on simultaneous diagonalization of Hermitian operators. So simultaneous diagonalization of Hermitian ops. Now, as we will emphasize towards the end, this is perhaps one of the most important ideas in quantum mechanics. It's the stuff that allows you to label and understand your state system. Basically, you need to diagonalize more than one operator most of the time. You can say, okay, you found the energy eigenstates, you're done. But if you find your energy eigenstates and you think you're done, maybe you are if you have all these energy eigenstates tabulated. But if you have a degeneracy, you have a lot of states that have the same energy, And what's different about them? They're certainly different because you got several states, but what's different about them you may not know unless you figure out that they have different physical properties. If they're different, something must be different about them. So you need more than one operator, and you're facing the problem of simultaneously diagonalizing things, because states cannot be characterized just by one property, one observable. It would be simple if you could, but life is not that simple. So you need more than one observable, and then you ask, when can they be simultaneously diagonalizable? Well, the statement is clear. If you have two operators, S and T, that belong to the linear operators in a vector space, they can be simultaneously diagonalized if there is a basis for which every basis vector is an eigenstate of this and an eigenstate of that. Common set of eigenstates. So they can be simultaneously diagonalized. Diagonalizable is that there is a basis where this basis is comprised of the eigenvectors of the operator. So this time you require more, that basis be at the same time a basis, a set of eigenvectors of this and a set of eigenvectors of the second one. So a necessary condition for simultaneous diagonalization is that they commute. Why is that? The fact that two operators commute or they don't commute is an issue that is basis independent. If they don't commute, the order gives something different, and that you can see in every basis. So if they don't commute and they're simultaneously diagonalizable, there would be a basis in which both are diagonal and they still wouldn't commute. But you know that diagonal matrices commute. So if two operators don't commute, they must not commute in any basis. Therefore, there can't be a basis in which both are at the same time diagonal. So you need, for simultaneous diagonalizable, that you need that S and T commute. Now, that may not be enough because not all operators can be diagonalized. So the fact that they commute is necessary, but not everything can be diagonalizable. Well, you've learned that every normal operator, every Hermitian operator is diagonalizable, and then you got now a claim of something that could possibly be true, is the fact that whenever you have two Hermitian operators, each one can be diagonalized by themselves, and they commute, there is a simultaneous set of eigenvectors of one and that are eigenvectors of the first and eigenvectors of the second. So the statement is that if S and T are commuting Hermitian operators, they can be simultaneously diagonalized. Simultaneously diagonalized. So this theorem would be quite easy to show if there would be no degeneracies, and that's what we're going to do first. But then we will consider the case of degeneracy. So I'm going to consider the following possibilities. Perhaps neither one has a degenerate spectrum. What does it mean, a degenerate spectrum? Same eigenvalue repeated many times. But that is a wishful thinking situation. So either both are non-degenerate, either one is non-degenerate and the other is degenerate, or both are degenerate. And that causes a very interesting complication. So let's consider there's going to be two cases, and it will suffice. In fact, it seemed that there are three, but two is enough to consider. There is no degeneracy no degeneracy in T. So suppose one operator has no degeneracy, and let's call it T. So that's one possibility, and then S may be degenerate or may not be degenerate. And the second possibility is that both S and T are degenerate. So I'll take care of case 1 first, and then we'll discuss case 2, and that will complete our discussion. So suppose there's no degeneracy in the spectrum of T. So case 1. So what does that mean? It means that T is non-degenerate. There's a basis U1 can be diagonalized to UN, orthonormal by the spectral theorem. And there's eigenvectors T, U, these are eigenvectors, lambda I, UI, and lambda I is different to lambda J when for I different from J. So all the eigenvalues, again, it's not summed here. All the eigenvalues are different. So what do we have? Well, each of those eigenvectors, each of the UIs that are eigenvectors, generate invariant subspaces. There are T invariant subspaces. So each one, each vector U1, you can imagine multiplying by all possible numbers, positive and negative, and that's an invariant one-dimensional subspace, because if you act with T, it's a T invariant space, you get a number times a vector there. So the question that you must ask now is, you want to know if these are simultaneous eigenvectors. So you want to figure out, what about S? How does S work with this thing? So you can act with S from the left. So you get STUI is equal to lambda I SUI. So here each UI generates an invariant subspace UI, T invariant. But S and T commute, so you have T SUI is equal to lambda I SUI. And look at that equation again. This says that this vector belongs to the invariant subspace UI, because it satisfies exactly the property that T acting on it is equal to lambda I UI. And it couldn't belong to any other of the subspaces because all the eigenvalues are different. So spaces that are in UI are the spaces, vectors that are in UI are precisely all those vectors that are left invariant by the action of T. They're scaled only. So this vector is also in UI. If this vector is in UI, SUI must be some number, WI times UI. And therefore, you've shown that UI is also an eigenvector of S, possibly with a different eigenvalue, of course. Because the only thing that you know is that SUI is in the space. You don't know how big it is. So then you've shown that indeed, these UIs that were eigenvalues, eigenfunctions, eigenstates of T are also eigenstates of S. And therefore, that's the statement of simultaneously diagonalizable. they have the common set of eigenvectors. So that's this part. And it's relatively straightforward. Now we have to do case 2. Case 2 is the interesting one. This time, you're going to have degeneracy. So we have to have a notation that is good for degeneracy. So if S is degeneracies, has degeneracies, what happens with this operator? It will have, remember, a degenerate operator has eigenstates that form higher than one-dimensional spaces. You know, if you have different eigenvalues, each one generates a one-dimensional operator invariant subspace. But if you have degeneracies, they're operators, they're spaces of higher dimension that are left invariant. So, for example, let UK denote the S invariant subspace of some dimension dk, which is greater or equal than 1. You see, in this time, I will go here first. We're going to define UK to be the set of all vectors so that SU is equal to lambda k u. And this will have dimension of UK is going to be dk. So look what's happening. Basically, the fact is that for some eigenvalue, say the kth eigenvalue, you just get several eigenvectors. So if you get several eigenvectors, not just scaled of each other, these eigenvectors corresponding to that eigenvalue span a space. It's a degenerate subspace. So you must imagine that as having a subspace of some dimensionality with some basis vectors that span this thing. And they all have the same eigenvector. Now, you should really have visualized this in a simple way. You have this subspace like a cone or something like that, in which every vector is an eigenvector. So every vector, when it's acted by S, is just scaled up. And all of them are scaled by the same amount. That is what this statement says. And corresponding to this thing, you have a basis of vectors, of these eigenvectors, and we'll call them UK1, the first one, the second, up to the dk1, because it's a subspace that we say has dimensionality dk. Okay, so look at this thing. Somebody tells you there's an operator, it has degenerate spectrum, you should start imagining all kinds of invariant subspaces of subdimensionality. If it has degeneracy, it's a degeneracy each time the dk is greater than 1. Because if it's one-dimensional, it's just one basis vector, one eigenvector, end of the story. Now, this thing, by the spectral theorem, this is an orthonormal basis. There's no problem when you have a degenerate subspace to find an orthonormal basis. The theorem guarantees it. So these are all orthonormal. So at the end of the day, you have a decomposition of the vector space, V, as U1 plus U2 plus maybe up to UM. And all these vector spaces, like U's here, they may have some with just no degeneracy and some with degeneracy 2, degeneracy 3, degeneracy 4. I don't know how much degeneracy, but they might have different degeneracies. Now, what do we say next? Well, the fact that S is a Hermitian operator says it just can be diagonalized, and we can find all these spaces and a basis for the whole thing. So the basis would look U1 of the first space up to U D1 of the first space. These are the basis vectors of the first plus the basis of the second, all the basis vectors U1 up to U dm of the mth space. Oh, this is the list. This is the basis of V. So I've listed the basis of V, which is a basis for U1, all these vectors, U2, all of this. So you see, we're not calculating anything. We're just trying to understand the picture. And why is this operator S diagonal in this basis? It's clear, because every vector here, every vector is an eigenvector of S. So when you act with S on any vector, you get that vector times a number. But that vector is orthogonal to all the rest. So when you have some U and S and another U, this gives you a vector proportional to U. And this is another vector. The matrix element is 0 because they're all orthogonal. So it should be obvious why this list produces something that is completely orthogonal. A diagonal matrix. So S in this basis looks like the diagonal matrix in which you have lambda 1 d1 times up to lambda m dm times. Now, I'll have to go until 2 to get the punchline. I apologize, but we can't stop right now. We're almost there, believe it or not. 2 more things. This basis is good, but actually another basis would also be good. I'll write this other basis would be a V1 acting on the U1 up to V1 acting on that U1 up to a Vm acting on this U1 up to Vm acting on that U1. This is M, this is Dm, and here is not U1, is UD1, 1, 1. You see, in the first collection of vectors, I act with a matrix or with an operator V1 up to here with an operator Vm, all of them, with Vk being an orthogonal, a unitary operator in UK. In every subspace, there are unitary operators, so you can have this basis and act with a unitary operator of the space U1 here, a unitary operator of the space U2 here, a unitary operator of the space UM here. Hope you're following. And what happens if this operator is unitary? This is still an orthonormal basis in U1. These are still an orthonormal basis in UM. And therefore, this is an orthonormal basis for the whole thing, because anyway, those different spaces are orthogonal to each other. This is an orthogonal decomposition. Everything is orthogonal to everything. So this basis would be equally good to represent the operator. Yes? Arbitrary unitary operators at this moment. Arbitrary. So here comes the catch as to the main property that now you want to establish, is that the spaces UK are also T invariant. You see, the spaces UK were defined to be S invariant subspaces. And now the main important thing is that they are also T invariant because they commute with that. So let's see why that is the case. Suppose U belongs to UK. And then let's look at the vector, examine the vector TU. What happens to TU? Well, you want to act on S, on TU to understand it. But S and T commute, so this is T, SU. But since U belongs to UK, that's the space with eigenvalue lambda k. So this is lambda k times U. So you have TU here. So TU acted with S gives you lambda k TU. So TU is in the invariant subspace UK. So this is what's happening here is now something very straightforward. You try to imagine how does the matrix T look in the basis that we had here. Here is this basis. How does this matrix T look? Well, this matrix keeps the invariant subspaces. So you have to think of it block diagonally. If it acts on the, here are the first vectors that you're considering, the U1. Well, if you act on the, with T on the U1 subspace, you stay in the U1 subspace. So you don't get anything else. So you must have zeros all over here, and you can have a matrix here. And if you act on the second UK, U2, you get a vector in U2. So it's orthogonal to all the other vectors. So you get a matrix here. And you get a matrix here. So actually, you get a block diagonal matrix in which the blocks correspond to the degeneracy. So if there's a degeneracy D1 here, it's a D1 times D1, and D2 times D2. So actually, you haven't simultaneously diagonalized them. That's the problem of degeneracy. You haven't. But you now have the tools, because this operator is Hermitian. Therefore, it's Hermitian here, and here, and here, and here. So you can diagonalize here. But what do you need for diagonalizing here? You need a unitary matrix. Call it V1. For here, you need another unitary matrix. Call it V2, Vn. And then this matrix becomes diagonal. But then what about the old matrix? Well, we just explained here that if you change the basis by unitary matrices, you don't change the first matrix. So actually, you succeeded. You now can diagonalize this without destroying your earlier result, and you manage to diagonalize the whole thing. So this is for two operators. In the notes, you'll see why it simply extends for 3, 4, and 5, or arbitrary number of operators. See you next time.